In this video, we're going to explore group transfer reactions and hydrolysis reactions. In the first type, group transfer reactions, we're going to investigate and learn how esters, thioesters, and amides are actually formed. Recall that an ester is a carbonyl which has an O attached to an R group coming off the carbonyl carbon. We have not previously looked at thioesters, but they are the exact same as esters, only with a sulfur in place of our oxygen. And also recall that amides consist of a nitrogen group attached to our carbonyl carbon. The mechanism by which these reactions take place involve the OH from a carboxylic acid and the hydrogen coming from either the alcohol, thiol, or the amine. In each case, the OH and the H are going to come together in order to form a water molecule. And then what will happen is the O from the carbonyl, the oxygen from the carbonyl, is going to come in and attach itself to the carbonyl carbon from the carboxylic acid. And in doing so, forms an ester, thioester, or an amide. And so in writing these reactions, for esters and thioesters, we're going to first write the carboxylic acid with its OH group pointing to the right, and the alcohol or the thiol pointing to the left. We'll then remove a water molecule by removing the OH from the carboxylic acid and the H from the alcohol or thiol. And we'll form a single bond where the OH and H were removed. When writing an amidation reaction, it's very, very similar. We're going to write our carboxylic acid on the left with the OH group pointing to the right, and we'll write our amine on the right with the NH group pointing to the left. We will remove the OH from the carboxylic acid and the H from the amine, and we will then form a single bond between the atoms from which the OH and the H were removed. Let's look at a couple examples first of the formation of some esters or thioesters. And so here we have a carboxylic acid plus an alcohol. And remember, our steps, we're going to take our OH from our carboxylic acid and our H from our alcohol, and those are going to form a water molecule in our product. The rest of the product will then consist of having our oxygen atom from our alcohol attaching itself to the carbon that the OH was removed from. The rest of both of the molecules simply gets pulled along and does not change. And so our resulting molecule is going to be our carboxylic acid that we started with, which looked just like this, but now with the OH removed. It is now going to be attached to the oxygen from the alcohol, and then the rest of the alcohol. And then recall that our other product is a water molecule. Let's look at another example with a thioester. Now this is something which at first glance looks a little bit more complicated. However, remember that really what we're looking at is just this portion of the molecules which are going to change and reform. The rest of the molecules are simply going to get pulled along in the reaction that occurs. And so, just as in with our ester above, for our thioester, the OH from our carboxylic acid and the H from our thiol are going to be removed in order to form water. And now our sulfur is going to come in and attach itself where the OH was, and the rest of our thiol is simply going to get pulled along. And we have not changed anything in the remainder of our carboxylic acid. And so we simply redraw our product as the carboxylic acid that was first there, minus the OH, and then we redraw our thiol attached to that, minus our hydrogen. And there we have our new thioester, plus water as our other product. Let's take a look at a couple of amidation reactions now. Amidation reactions occur in the same way that esterification and thioesterification reactions occur. So once again, our OH from our carboxylic acid and our H from our amine are going to be removed in order to form water, and our nitrogen is going to bond with our carbonyl carbon. And the rest of the carboxylic acid and amine simply get pulled along for the ride. And so we redraw our carboxylic acid without the OH. Instead, we attach it to our nitrogen, which then has the rest of the amine attached to that. Let's look at an example with a secondary amine. Again, this is something that looks a little bit hairier and a little bit more complicated, but the basic concept is the exact same. The OH from our carboxylic acid will be removed along with the H from the amine in order to form water, and our nitrogen is going to bond to our carbonyl carbon, and the rest of both of the molecules will be pulled along to form our final amide. And so for our product, we're going to redraw our carboxylic acid, again without the OH attached, but we will have the nitrogen from our amine and everything else that came with the amine, plus water as our other product. Let's look at one more example. Here we have our carboxylic acid reacting now with a tertiary amine. In this case, there will be no reaction that occurs. Take a couple seconds now and ask yourself why. Figure out why an amidation reaction cannot occur with a tertiary amine. Pause the video if you would like, and think about this for a minute. Think you've got it? That's right. There is no hydrogen on a tertiary amine to form our water. Therefore, the group transfer reaction cannot occur, because that water formation is one of the driving forces of this reaction. Without that hydrogen on a tertiary amine, we get no reaction. Hydrolysis reactions are incredibly common reactions in biochemistry. They're the first step in the digestion of proteins to amino acids. They're the first step in conversion of fats into fatty acids and glycerol, and they also convert starch into glucose. Basically, hydrolysis reactions are simply the exact opposite of group transfer reactions. In a hydrolysis reaction, we're going to take esters, thioesters, and amides and break them into their constituent carboxylic acid and alcohols, thiols, or amines. And so in the case of an ester, We will hydrolyze it, we will add water to form our carboxylic acid and our alcohol. Thioesters will hydrolyze to form the carboxylic acid and the thiol. Amides will hydrolyze to form not the carboxylic acid in this case, but what we call the carboxylate ion, which is simply the carboxylic acid with the H removed, forming a negative ion. They'll also form the conjugate acid of whatever amine we had. That's just the amine with an extra hydrogen attached, forming the positive ion. But the basics are still the same. The amide is going to break up into its constituent parts. In order to predict the products of hydrolysis reactions, we're going to break our single bond between the carbonyl carbon and the heteroatom. And so that single bond between the carbonyl carbon and the oxygen in the case of an ester, the sulfur in the case of a thioester, and the nitrogen in the case of an amide. We break that bond, and then we add an OH group to the carbonyl carbon in order to form the carboxylic acid from one. And we'll add a hydrogen atom to the heteroatom to form the alcohol, thio, or amine of our other product. And just recall that if it is an amide, the resultant amine and carboxylic acid will react in order to form the carboxylate ion and the conjugate acid of the amide. And so let's look at some examples. So here in our first example, we have an ester, which is going to undergo hydrolysis. When it undergoes hydrolysis, our bond between the carbonyl carbon and the heteroatom is going to be broken. And so we can then draw our products. The carbonyl becomes our carboxylic acid. And then we have an alcohol on the other side. We're going to then attach the H to that oxygen, and the rest of the compound still comes along. Let's look at an example of a thioester. Again, this is one that looks fairly complicated, but it really is pretty simple. We're going to hydrolyze the compound, and we are then going to break our bond between the carbonyl carbon and our sulfur. And when we draw our products, everything else still comes along for the ride. We're going to form our carboxylic acid by adding our OH here, and our thiol forms by adding an H onto our sulfur. For our last example, we're going to look at the hydrolysis of an amide. Again, the process is the exact same, where we're going to break our bond between our carbonyl carbon and our heteroatom, and we're going to reform our products. Although we do have to recognize here that an acid-base reaction is going to occur between our carboxylic acid and our amine. And so in this case, the amine, acting as a base, is going to remove our proton from our carboxylic acid. And so our final products are going to be the carboxylate ion and the conjugate acid of the amine. And so in this video, we've explored both group transfer and hydrolysis reactions. Remember that no matter if we're talking about an ester, a thioester, or an amide, the process is the same, in which we are going to have some sort of carboxylic acid reacting with our alcohol, our thiol, or our amine. And in this case, I'll just represent those as a Y. if Y is an oxygen, that's our alcohol. A sulfur is a thiol. And an N, we would have our amine. And in all of these examples, the OH from the carboxylic acid will form water with the H from the alcohol, thiol, or amine. And then the oxygen, sulfur, or nitrogen will bond with the carbonyl carbon. And the remainder of the molecules simply get dragged along for the ride. And then in a hydrolysis reaction, we break our bond between our carbonyl and our heteroatom in order to reform our carboxylic acid and our alcohol, thiol, or amine. Again, just remembering that in the case of the amine, the final products will actually be the carboxylate ion and the conjugate acid of the amine. And so I hope this video about group transfer reactions and hydrolysis reactions has been helpful. If you do need some additional assistance, be sure to come see me or look at any other resources. And be sure to look at the practice problems on the website.